Okay, in this video, we're going to talk about the z-score, which is a number that's related to a particular value of data that's normally distributed, and then we'll talk about using it to calculate percentiles. Okay, so say a lot of times when you're talking about normally distributed data, the nice thing about it is that if you know the mean and the standard deviation, you could tell a lot about how your data is arranged. Okay? And so let's say that we've got an example, I don't know, the salary of employees is normally distributed with mean, say, $50,000 and standard deviation let's say $10,000. Okay? So in the last class, we talked about using standard deviation to compare different values. And when we did this, we would take a data value, we would subtract the mean, and divide by the standard deviation. Right? And if you remember, we computed this value for example, different things, and then used these values to compare. So we're going to give these a name. So this is called, we usually call it Z, and this is called the z-score. Of a data value. Okay? And so, for example, in this case where we've got the salary of our employees normally distributed with mean 50,000, standard deviation 10,000, what would you say about someone who makes, say, $70,000 a year, has a z-score of 70,000 minus 50,000 minus the mean divided by the standard deviation. So z equals 2. Right? 70,000 minus 50,000 gives you 20,000. Divide by 10,000, you get 2. Okay? And so when we talked about this last class, we talked about the z-scores kind of telling us how many standard deviations to the left or to the right of the mean we were, right? So this person's salary is 2 standard deviations above the mean or to the right of the mean, okay? And so that's all well and good. The nice thing about normally distributed data, if we know our data is normally distributed, we can actually take this a step further, okay? And so included with this lecture, you'll see that there's a table of values. So this is the document that's included with the lecture. You can't necessarily see it on my camera, but you've got access to that document and you can print it out or look at it on your computer. But what this does, this document has percentiles from z-scores, okay? And so let's see. I'm going to erase everything. If our data is normally distributed, we can find, again, with some kind of statistical inaccuracy, this is not going to be perfectly, but we can find approximately the percentage of values that are less than a particular data value. Okay, so for example, in that past example, the one that we just looked at, what percentage of employees make less than $70,000? Okay, so we know that the mean is 50,000. We know the standard deviation is 10,000. So we know the z-score of 70,000 minus 50,000 over 10,000 is 2. But this table lets us look up a particular z-score and find the percentage that corresponds to it. So if you look at the table, and maybe you can see this, if you look at 2, the z-score of 2, right here, you can see that the corresponding percentage is 97.73. Okay? So 97.73% of people at this company make less than 70,000. Okay? So once you know the z-score, if the data is normally distributed, you can find the percentage, the percentile, the percentage that are less than that particular value. Okay? So this person makes more than 97.73% of the people at the company. And you could actually take this kind of a step further and do even more interesting things. So say you wanted to know, and again, going back to mean, 50,000, standard deviation, 10,000 in this particular example. What percentage of people make more than 70, or well, let's do it completely. Let's do more than 55,000. Okay? So you can ask yourself, what percentage make more than 55,000? Same idea. We're going to find the z-score. Right? We always convert these into z-scores because that z-score is going to give us a way of comparing to these actual percentiles. So 55,000 minus 50,000 divided by 10,000. Right? So our value minus our mean divided by our standard deviation gives us a z-score of 0.5. And if you look at the table, under 0.5, we've got 69.15. So 69.15% make less than 55,000, which isn't exactly what the question asked, right? The question asked, what percentage of people make more than 55,000? Well, if 69.15% make less than 55,000, we can subtract that from 100%. So 100 minus 69.15, which is equal to 30.85%, make more than 55,000. Okay? So that's relatively easy, right? If we know how many make less, we can find how many make more. We can even find how many make in a particular range, right? So how many make between 55,000 and 70,000. Right? So we've already found the z-scores for each of these. We know that 69.15% make less than 55,000 because it had a z-score of 0.5. We know that 97.73% make less than 70,000. And so if you want to know how many make between 55,000 and 70,000, well, you've got the number that make less than 70,000, the number that make less than 55,000, if you subtract these, you're going to find the amount that are in between, right? Because people who make less than 55,000 also make less than 70,000, okay? So subtracting them, 97.73 minus 69.15, that gives us, that one I need a calculator for. 97.73 minus 69.15 gives us 28.58%. And so 28.58% make between 55,000 and 70,000. Okay? And so that gives you an idea of the range. Again, anything that's normally distributed, if you know the mean and the standard deviation, you can do these calculations and actually get these percentages. Okay? So in the next lecture, we'll talk about the empirical rule, which is based on this and gives us some nice rules of thumb about standard deviation.